Hello. Today we are moving to the last section of this chapter. This section is spanning trees and a shortest path algorithm. This is chapter 10, Theory of Graphs and Trees. This section is little longer, so I split this into two parts. The first part is here, and the second part will be taught in the next day. This section includes three important algorithms. Um, the first algorithm is Kruskal's algorithm, and then we learn Prime's algorithm, and after that we learn Dijkstra's algorithm. Dijkstra's algorithm is a shortest path algorithm, so that's why it says spanning trees. We learn spanning trees at the beginning, and then we learn a shortest path algorithm, which is world famous Dijkstra's algorithm. All right, now let's learn about spanning trees. This is the definition of a spanning tree. Spanning tree for a graph G is a subgraph of G. Spanning tree is a subgraph that contains every vertex of G. All right, and then it's a tree. Okay, so for a given graph, you can compute a spanning tree. This spanning tree is a subgraph of G that should contains all the vertices, and then it should be a tree. All right, we have the first proposition 10.6.1. Every connected graph has a spanning tree. Part 2 of the proposition is any two spanning trees for a graph have same number of edges. All right. Let's discuss the first proposition. Every connected graph has a spanning tree. So that's easy. Let's say this is the given graph to you. Just consider any graph that you would like. Let's say this is the given graph to you. This is a graph of 4 vertices and let's say 5 vertices. It has 5 vertices and then it has 6 edges. The spanning tree is a subgraph. It's a subgraph of this graph, which is G here. Let me denote that as G. A subgraph of G, it should contain every vertex of G. Alright, so it should contain every vertex of G. So it should have these vertices. I'm sorry, I just drew the edges too. Just forget about the edges for now. It has these vertices, and then you have to connect these vertices to get a spanning tree. All right. Let me check how to get the spanning tree here. That I'm gonna teach you later. I'm gonna give you the details later. For now, let's make a spanning tree. A spanning tree is a connected graph, something like this. Okay, so this is a connected graph, but it doesn't have circuits. The most important thing is it doesn't have circuits. In order to be a tree, it should not have circuits. All right. So this we learned this early. Let me mark it here. Trees do not have circuits. Okay, trees do not have circuits. So if you consider this, it has circuits. See, it has circuits. This is a circuit, that's a circuit. So you have to get rid of these circuits. How do you get rid of these circuits? How do you get rid of these circuits? You can just ignore this edge. So then that will eliminate this circuit. So you ignore that. So that will eliminate that circuit. You ignore this edge. So that will eliminate this circuit. All right. So what you get is a spanning tree. So this is a spanning tree. Okay, I'm going to teach you how to get a spanning tree later. For now, just keep in your mind that spanning tree should have all the vertices, and then it should not have circuits. All right. The first point of the preposition says every connected graph has a spanning tree. All right. For every connected graph, this is a connected graph, you can just get the resulted spanning tree. One should delete edges. When you delete edges, you have to make sure that you do not make the graph disconnected. All right. Sometimes deleting edges might make the graph disconnected. As an example, if you delete this edge and that edge, so that will make a disconnected graph. So you don't do that. The graph should be connected, otherwise it won't be a tree. Trees are connected. All right. You learn trees and forest early. Trees are connected. If trees are not connected, that's called a forest. All right. So that part is okay. And then the second part, any two spanning tree for a graph have same number of edges. Okay, so this is a spanning tree 1. Let's say this is spanning tree 1. Now I'm going to get another spanning tree. For this spanning tree, I'm going to delete some other edges. Now what I'm going to do, I'm going to delete some other edges. Let's say I'm going to delete this edge and that edge. All right, let me use a different arrow. Let me do something like this. I will use this color like that, and then I will mark this. Circuit. Give me a second. What I'm doing here is, let me mark both here. So red, these red edges are deleted, so you get that red color arrow. And then here orange, so you get this orange color arrow. Okay, so the resulted spanning tree should look like this. You should have all the vertices as it is, but the edges are different. Okay, so this is the corresponding spanning tree here. That's also a tree. So that's the second spanning tree. You can see spanning trees are not unique. All right, you can make different spanning trees. Okay, this says any two spanning trees for a graph have same number of edges. So this is spanning tree number 1. Spanning tree number 2, just count number of edges. 1, 2, 3, 4. 4 edges. 1, 2, say 2, 3, 4. Here also 4 edges. Okay, edges are equal for both spanning trees. So that is number 2 of the preposition. All right, you understand number 1 and number 2 of the preposition. Let's move to the next slide. This is example 10.6.1, spanning tree. Find all spanning trees for the graph G pictured below. Okay, so we're going to compute all the spanning trees here. Like I did before, first of all, you have to understand whether it has circuits. I see it has a circuit, so this is the circuit it has. Let me mark that circuit. Okay, this is the circuit it has. So you have to delete edges of these circuits one at a time. Okay, first I can delete this edge. All right, so you get this spanning tree. The spanning trees are having same number of vertices. In the next case, you delete that. You get this spanning tree. And finally, you delete this. So you get this spanning tree. You can think of 3 spanning trees here. Okay, so those are the 3 spanning trees for this example. All right, so here I give you the description, how it comes. The graph G has one circuit, like I showed you before. The circuit is here, which is V2, V1, V4, V2, V1, yes, that's the circuit. Then you remove one edge at a time. All right, so that will give you spanning trees. Thus, these are the spanning trees that we discussed earlier. These are the spanning trees that we discussed earlier. All right, we discussed this information early, so just move to the next slide. Now we're going to compute something else, which is the core of spanning trees. Now we are going to compute the minimum spanning tree, which is the meaningful aspect of this trees, of these trees. All right, so let me explain this example. The graph of the routes allowed by the US Federal Aviation Authority, shown in figure 10.6.1, can be annotated by adding the distances between each pair of cities. So there are a few cities. How many cities? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 cities. So there are flights between these cities. So edges represent the flights between cities. All right. Now what you do is you add distances. You add distances. okay, between each pair of cities. Let's go to the next slide. Here are the distances between cities. Minneapolis to Nashville, 695 miles, and the Minneapolis to Chicago, 355 miles, and Detroit to Cincinnati, 230 miles, and so on. All right, so here you have all the mutual distances between cities. All right, so now before flying, you know how far between cities. All right, so go down. Now, this is a weighted tree. You know that it's a weighted tree. Sorry, it's a weighted graph because each edge has a corresponding weight. Now, we're going to talk about spanning tree for this aspect. All right. First point, suppose the airline company wants to serve all the cities shown. Okay, so that's true. Airline companies want to serve all the cities. But with a route system that minimizes the total mileage of the system as a whole. Okay, so there should be a route system that minimizes the total mileage. That's true. Okay, there should be a way of traveling that minimizes the mileage. As an example, if there's a flight from Nashville to Cincinnati, that if that passes through Louisville, then that flight can stop at Louisville, all right, and then unload and load passengers and goods, and then go back to Cincinnati. From Cincinnati to the next destination, from that destination to the next destination, and so on. Or the minimum spanning tree is the tree that connects all the cities with the minimum distance. Okay, that connects all the cities with the minimum distance. It is good to know that. So they can just operate airlines with cheap cost. All right. So that is point 1, the first bullet. The second bullet, if the system contains circuits, remove of an edge from the circuit. If it has circuits, there's a problem maker. So you have to remove an edge from the circuit. Okay, would not affect the person's ability to reach every city in the system. That's true. As an example, there's a circuit between these 3 cities. Okay, there's a circuit between these 3 cities. Since it is a circuit, so you can reach to one destination from another destination. You can reach to this destination from this destination in 2 ways. Either this way, directly from Detroit to Louisville, or maybe you can go to Cincinnati first and then come back to Louisville. All right. Whenever there are circuits, you can just have 2 paths reaching between cities. So that's too much. That's extra, unnecessary. So what you do is you just whenever you see a circuit, you just delete one edge to make sure you just have minimum total distance. All right. In that case, you can either delete this edge, or that edge, any edge you would like. Okay. Once you delete one edge, then still you can just travel between cities without any problem, but the total distance is less. All right. So let's move to the point. Let me read this again. If the system contains circuits, remove of an edge from the circuit would not affect the person's ability to reach every city in the system from every other, but it would reduce the total mileage of the system. All right, so that's clear to everybody. That would not affect. All right, but it just reduces the total mileage of the system. Or once you do these 2 points, once you do that and that, once you apply these 2 bullets, then what you get is a tree. Such a system is called a tree. All right. And then the next bullet is we have to ensure the graph is connected. while removing circuits. That's true. If you just disconnect the graph is no longer be a tree. Okay, the graph no longer be a tree. All right, so keep that in mind. You have to make sure that the graph is connected. Ensure the graph is connected while removing circuits. All right, so those are the important bullets in the previous slide. Let's move to the next slide. In the next slide, we're gonna learn minimum spanning trees. A graph whose edges are labeled with numbers known as weights is called a weighted graph. This is the first time you learn weighted graphs. What are the weighted graphs? It's a graph whose edges are labeled with numbers. Those are known as weights. Let's say you have a graph like this. There are some edges. Sorry, there are some vertices. Now you have some edges between these vertices. So there are some the weights labels. This is 75, 43, 99, 16. All right. So this is a weighted graph. This is called a weighted graph. Okay, that's called a weighted graph. Okay. More generally, a minimum weighted spanning tree, or simply a minimum spanning tree, is a spanning tree for which the sum of the weights of all the edges is small as possible. Okay, now we are moving forward with minimum weighted spanning tree. Minimum weight spanning tree is a spanning tree for which the sum of the weights of all the edges is as small as possible. So you have to sum the edges such that you get the small number. All right. So for this graph, you can see there's a circuit. So you can just ignore an edge to get the spanning tree out of that. When you ignore the edge, you have to make sure you ignore the edge with the most weight. Okay, so edge with the most weight. That is the edge with the most weight. This is the largest. Largest weight. Largest weight in the circuit. Okay, so this is the largest weight in the circuit. This is the largest weight in the circuit. So you just ignore that edge. Yes, you ignore that edge. So that will give you the minimum spanning tree. All right. Now there's a definition here that we'll already discuss. Let me to present that as a definition. A weighted graph is a graph which each edge has an associated positive real number weight. We have positive real number weight. All right. The sum of the weights of all the edges is the total weight. The sum of the weight is called the total weight of the graph. A minimum spanning tree for a connected weighted graph is a spanning tree that has the least possible total weight compared to the other. Let me mark like that. Least possible total weight compared to all other spanning trees of the graph. All right. If G is a weighted graph and E is an edge of G, then WE denotes the weight of E and WG denotes the total weight of G. All right, those are notations. Don't worry about that. If the graph is G and if E is an edge of the graph G, we use this notation WE to denote the weight of E, and then we denote this to denote, we denote this notation to use total weight of G. All right, those are just two notations. Don't worry about them. Okay, let's move to the next slide. Kruskal's algorithm can be used to compute spanning trees of a given graph. Let me read this slide first. In Kruskal's algorithm, the edges of connected weighted graph, those are the properties that the graph should satisfy. The graph should be connected and weighted. Okay, those are the two properties that the graph should satisfy. In Kruskal's algorithm, the edges of a connected weighted graph are examined one by one in order to increase the weight. At each stage, the edge being examined is added. All right, at each step we just examine an edge and then we just add that edge into the spanning tree to what will become the minimum spanning tree, provided that this addition does not create circuits. So we have to get rid of circuits. So you have to make sure that we do not make circuits. If we make circuits, then that's no longer be a tree. If we make a circuit, then the graph is no longer be a tree. All right. After n-1 edges have been added, these edges together with the vertices of the graph form a minimum spanning tree. Okay, you just add n-1 edges, then these edges together with the vertices make a minimum spanning tree. All right, then there's a theorem. This theorem is not much important, but I will read it. When a connected weighted graph is input to Kruskal's algorithm, the output is a minimum spanning tree. Okay, that's what the Kruskal's algorithm does. Okay, so you input a graph which should be connected and weighted, then the Kruskal algorithm will give you minimum spanning tree. All right, so this is the Kruskal's algorithm. Let me read the algorithm. The input is connected weighted graph with n vertices. All right. The body of the algorithm: build a subgraph T of G to consist of all the vertices of G with edges added in order of increasing weight. At each stage, let M be the number of edges of T. All right. So we just initialize this subgraph T of G, which consists all the vertices of G. Okay, T consists all the vertices of G. And then we add edges into T. First we have to initialize T T to have all the vertices of G. All right, as an example, let me give an example here. Just consider this is the given graph to you. This is not a spanning tree because it has circuits. Let's say these weights are 2, 3, 4, 1, 7, 4. Okay, these are the weights. Now what you do in the first step, just you initialize step number 1. You initialize these vertices into T. I'm sorry, only vertices. Okay, that's step number 1. And in step number 2, we define this E be the set of all the edges in G. All right. In step number 3, we just keep on adding edges. Find an edge E in E of least weight. In this graph, what has the least weight? This has the least weight. All right. That one has the least weight. That has the least weight. Now, since it's the least weight, now we just delete that edge from E. We delete that edge from E because we are not interested that anymore because we have already considered that. Then the step 3C, if adding E to the edge set T does not produce a circuit. No, it does not produce a circuit. All right. So we just add that into the spanning tree. Okay, so that's the first iteration, and then just go to the second iteration. Okay, then in the second iteration we have these vertices, and then we already have that edge, and then we have to find the next least edge. Next least edge is this. All right, now we just choose that, find an edge E in E of the least weight. Now the green one is the least weight because we already removed one from the edge list. E is the edge list, so we have already removed one, so 2 is the least. And then we remove 2 from the set, and then if adding E to the edge set T does not produce a circuit, it does not produce a circuit. The 2 is right here, so you can simply add 2 with weight 2. So that doesn't add a circuit. So we proceed and then go to iteration 3. Now you have these 5 vertices. You already added that. You already added this. And then you check the next least. Next least should be 3. So you add 3 into this graph, which is 3 right here. And then find the next least. Next least is either this 4 or that 4. You could choose any 4 you would like. I choose this 4. So you just add that into the let me mark iteration 4. In iteration 4 you have this, that. You already added that, you already added this, you already added that, and then you add this 4. I'm sorry, there's a problem. You can't add this 4 you can't add this 4. Why? If you add that 4, it makes a circuit. Okay, so this is a circuit, so that's not a spanning tree anymore, so you can't add that 4. Because of that reason, you have to consider this 4. All right, you have to consider that 4. You can simply add that 4 to make the spanning tree. So this is the spanning tree. Now how the algorithm terminates. Now you have to choose the other two edges, this and that. You have to consider the remaining two edges. Once you add the remaining two edges, you make circuits. Once you add that, you make a circuit here. Once you add this, you make a circuit there. So that means you have to execute the algorithm. You have to abort the algorithm at this situation. All right, so you have to stop the algorithm, right? So this is the spanning tree. So the final tree is this spanning tree. The method that we used here is Kruskal's method. All right, so that is the spanning tree. Let me separate these. All right, so that is the given algorithm. Now we are going to discuss an example. Here we have the same example with the cities, and then you have the distances between cities too. Now we are going to use the Kruskal's algorithm. Let me mark these cities here. Let me start from here. This is the first city, and another city here, another city there, and another city here, another city there, Cincinnati here, Detroit there, and Nashville here. All right. Let me select this and make it small. And I'm going to make some copies of that, so I can just copy and paste them. Copy. Insert. Paste. And then let me make another copy of that. make another copy maybe here. All right, so I have enough copies. So let me make this a little smaller. Okay, so I have the vertex set now. I have to choose the smallest edge, which is this, right? So I have to just add an edge between these two. All right, and then we have to find the next smallest the next smallest. Already we have these two cities joined. So this is the length is 74. The length is 74. And the next least is 83. So you could choose that, Cincinnati and Louisville. So those are right here. So you add that, Cincinnati and Louisville, which is 83. All right, and then you come here. In this you already added this edge 74. You already added that edge, which is 83, and then find the next smallest edge, which is 151. So you could add that. That means this edge. Okay, so then move to the next step. I'm sorry. This is already added. I'm using the cross-cult method, right? This is 74, 83, and here 151. This is 151. And then what is the next smallest? 230. I don't know, add 230, which is between these two cities. Okay, and then go forward. Let me get this close. Let me make a copy of that. Okay, now we already added this 74. I'm sorry. We already added this 83. You already did that 151, and then you already added Detroit and Cincinnati 230. This is 230. And then find the next least weight. You have a few more 200s. You have 242. Louisville, between Louisville and St. Louis. So that means you add that, which is 242. All right, let me make another copy of this. Let me put it here. Now in this case, the next smallest is, we have two 200s. So this is the next smallest, 262 between St. Louis and Chicago. It goes like this, which is 262. Okay, so in the next one you have that one, 74, that one, this one, that. This is 230, 83, 151, 242, 262, 74. And the next smallest is this, but the problem is we can't add that. Let me mark that with a different color. We can't add that between Chicago and Louisville. Okay, Chicago and Louisville, if we add that, that will make a circuit. Okay, so we can't add that because it makes a circuit, so we have to ignore that. So let me ignore that. And then the next smallest is 348. That again we can't add that. 348 between Milwaukee and Louisville. Again, that will make a circuit. If you add that, that will make a circuit, so it's impossible. So the next smallest is 355, which is between Chicago and Minneapolis, like this. Okay, so that is the resulted spanning tree. $355. All right, so this is the spanning tree. The method we use is called Kruskals method. Kruskals. We use the Kruskals algorithm. All right. Let me delete. Give me a second. Let me think what I can do. So to save space, I'm gonna take this little leftward, and then I'm gonna delete this. And then I'm gonna copy that one into the next slide. All right, so this is the corresponding spanning tree, minimum spanning tree. Now this slide explains all the weights and what are the added edges and what are the non-added edges. You can understand them. We didn't add these numbers, 348, 269, and then so you can read this and understand. Give me a second. All right, go down, and then this is the corresponding tree that we obtained right here. Okay, the same tree. in a new slide. That is the end of the class. Today we learn a Kruskal's algorithm that can be used to compute a minimum spanning tree. In the next day, we're gonna learn another two methods, another two algorithms. The first algorithm is Prime's algorithm, and then we're gonna learn Dijkstra's algorithm, which can be used to compute a shortest path of a given weighted graph. All right. So that's all for the day. Thank you.